then these two become 0, right? So we can get rid of them. And then this one equal to this one. And we follow this one. Okay, because original is this one, and then we add another one, so we add this one first, and this. So same thing, this one, we add another one, so we do these two first. So we get a 0 vector, and then 0 vector add the other vectors. This one remains to be this vector. So we have negative u equal to negative 1 times u. Okay. So with that, let's look at the other. For example, 0 times u equal to 0. This is what we want to prove. So 0 times u, it could be 1 plus, or 1 plus negative 1. Okay, it will be u plus negative 1 u. So this one is already, we already proved that. Sorry. Okay, and so this one is 0. Right? Right? From here, so 0 times u equal to this one, and equal to this one, equal to this one. This is we just proved. This one equal to this one, right? And for every element we have an inverse, and to be 0 vector. So that's the first one. Right? The second one. If u plus v equal to 0, then v equal to negative u. So it's like u plus v, okay, equal to 0, u plus w equal to 0. We want to prove v equal to w. Okay, the uniqueness of like inverse. So we u plus v, just like what I said, like okay, we just add a negative u here on the both sides. Originally, it's like this. And then we make it like a negative u plus v plus equal to negative u plus w. So this one equal to 0. So 0 plus v equal to 0 plus w. So we know v equal to w. Right? So the key is to try to apply the actions on each step to obtain whatever you want to prove. So there are simple actions. a simple theorem. Well, actually, in mathematics, we don't call them theorems. At most, we call them lemma. Okay, because usually if it's theorem, it's big thing. Okay, it's something very big. Okay, for example, Cramer's rule, or like those type of stuff. Like we can call them theorem. For things like this, they are really not that large. Okay, so we finish the definition of vector space. Then we need to talk about subspace. Okay, subspace. Okay, based on the term, obviously it's a subset of a vector space, right? It must be a subset of a vector space. Okay? So if S is a subset of V, first it's non-empty. Okay? And satisfy following conditions, then S is called a subspace of V. So it's not just a subset, it has to satisfy some properties. Okay, this is relatively easier. Okay, remember, V is already a vector space, so V already satisfies all those 10 actions. Okay, so for S, okay, for this non-zero subset to be a subspace of V, okay, S has to satisfy the following two conditions. For the first, for any vector uv in S, U plus V, okay, the addition, okay, must fall back into this subspace. Okay, so that's the first thing. The closure of addition still holds for this subspace. Second, for any scalar A and the vector U, AU in S. So this it multiply like a element multiplied by scalar means still fall in this subspace. Okay, so according to the definition, okay, to verify whether a subset of vector space is a subspace or not, we just verify the closure of addition and the scalar multiplication. This is good enough because those 10 actions are already given. Okay? So for vector space, V and this is not an empty set. This is a set with a zero vector. Okay? These two are its subspace. Okay? So this set that contains only the zero vector is called the zero space. Okay, and any subspace of V except V itself is called a proper subspace. I mean, this is just like a subset, right? If you call a set a proper subset of another set, I mean, they have to be different, right? They have to be, the proper subset has to be smaller than the original set, right? So the proper subspace, I mean, is similar, okay? So, and also, zero belongs to any vector space and subspace. Why? Why do we say that? Because, you know, the scalar multiplication has to be close, right? So if because it's the subspace is non-zero, right? Not empty. So you give me any element from this subspace. I multiply this element by a zero scalar. We end up with a zero vector, right? So that zero vector, okay, you know, according to these two conditions, okay, this one, this 0 times U has to be in S, right? So in other words, the zero vector has to be in any subspace. Okay? According to that condition. So, let's give some examples. Okay. This S should be x1, x2, x3 transpose. So it's a column vector, okay, with 3 elements. And in this example, x1 equal to x2. So we have this requirement, okay, for the set S. Okay, so S is a subspace of R3. So first, S is not empty. So this is something you have to verify, okay, when you check if something is a subspace, because after all, subspace has to be non-empty, right? So one thing very simple is that you can check easily that 0, 0, 0, the zero vector, okay, is in S. So S is non-empty. And then, okay, if you have x1, x2, x3, okay, x is this one. Hello? Okay. We have like x1 equal to x2. So for any scalar C, okay, so in other words, like you multiply x with a C, cx1, cx2, cx3, okay, obviously cx1 equal to cx2, right? So the resulting cx must fall into this S as well. Okay, so it's so this S is closed under scalar multiplication. So how about like addition? So if x is this one, y is this one, if you add up these two, then the x plus y is this one, right? But since we know x1 equal to x2 and the y1 equal to y2, so x1 plus y1 must equal to x2 plus y2. So obviously x plus y belongs to S again. So it is closed under addition. So we know like S is like a subspace of R3. And it is also proper subspace of R3 because they are obviously like some vectors that are in R3 but not in S, right? Okay. So another example, then S to be A, which is like R 2 by 2. So this is really like a matrix of 2 by 2. Okay. So in this matrix, A12 equal to negative A21. So let me finish this example because like yeah, I don't want to, you know. So this is these two. Okay, these two elements. Okay, they are negation to each other. Okay, so this one forms a subspace of R22, 2 by 2. So obviously, like again, you can see 0, 0, 0, 0. This one is in S, right? So it's non-empty, right? It's non-empty. And then, you know, for scalar multiplication, so A11, A12, A21, A22. So if you multiply alpha, okay, the result will be alpha A11, alpha A21, 12, and the alpha A21, and the alpha A22. So obviously, since A12 and A21 are negation to each other, so you multiply alpha, obviously this property still holds. right? They are still negation to each other. Okay, so it's like this is the S is closed under scalar multiplication. How about addition? If it's like x11, x12, x21, x22, we have this capital X, capital Y to be y11, y12, y21, and y22. And if you add them up, it will be x11 plus y11, x12 plus y12, x21 plus y21, and x22 plus y22. So because x12 is and x21 are negation to each other, y12 and y21 are negation to each other. So if you add up these two elements, they are negation to each other, right? So the addition, okay, if this is one element in S, this is one element in S, the addition is one element in S. So the addition is closed under like the addition is closed under in S. So S is subspace R22. So here, okay, of course we are assuming the R22, R2 times 2, and the R3, they are already vector space. So we did not verify if they are vector space, but they are really like easy to verify. Okay, so yeah, that's about it. So we have more examples, but I think like the following examples are like more challenging. But I think we will do that next week. We are running out of time. I need to run to another meeting. Okay, so again, let me remind you. Okay, we will have quiz at the beginning of lecture next week. Okay, I hope I can get this issue resolved, and the range for the quiz 2 will be, supposedly like the problem set, the second problem set, second practice questions. Okay, and that's it for today. Any question? If no question, I'll see you next week. Okay? And I think like next week we have 2 lectures, right? Like one lecture like on Wednesday and one lecture on Saturday, because like the week after next I will be in Vienna for like student recruitment. Okay? 所以下礼拜的课，因为我人在越南招生，所以我下礼拜课，我上次有跟大家讨论，会移到前一个礼拜六，所以下个礼拜3有一个课，礼拜6有一个课，先跟大家讲一声 ，OK？ 好。礼拜6了。